For 100 years, physics has been staring at a broken bridge. On one side, we have the incredibly precise rules of quantum mechanics governing the microscopic world. On the other, the macro-scale expansion of the universe, driven by a mysterious force we call dark energy. The two sides refuse to connect. A new proposition suggests the problem is how we picture space itself. This framework views reality as a dense, three-dimensional pixel grid, a discrete lattice of geometric cells constantly computing their next state. The idea of treating the universe as a computational entity governed by simple rules goes back decades. Mathematicians have long studied cellular automata, grids where basic local rules generate incredibly complex, lifelike patterns. The Poole Manifold takes this concept into 3 dimensions. It describes a vast lattice where every single cell looks exclusively at its 26 immediate neighbors. Based entirely on the states of those neighbors, the cell decides whether to turn on or turn off. Under this model, particles, physical forces, and even biology are emergent configurations. They function as different pressure venting patterns, or masks, operating on top of a single underlying geometry. If this manifold accurately describes reality, the entire universe operates as one unified computing engine. The laws of physics are the algorithms that naturally emerge from the grid. Down at the microscopic scale, the lattice runs a harsh accounting system. Every cell constantly tallies up its active neighbors to determine its own survival in the next moment. This diagram illustrates a process called prime resonance sharpening. Instead of reacting to the raw noise of the grid, this filter forces local energy states to snap to specific prime numbers, creating clear, ordered output streams. By locking onto these frequencies, chaotic energy crystallizes. It forms stable, localized wave packets that pulse consistently over thousands of generations, without dissolving. As these stable packets propagate through the lattice, they push against the surrounding geometry. This outward pressure creates a distance-dependent interaction between packets. Fundamental matter and physical forces represent the byproducts of this geometric friction. When stable wave packets interact predictably, they can be organized. They route themselves into continuous, flowing, three-dimensional pathways, functioning exactly like physical computer hardware. If you collide these flow pathways at specific angles, you create blowout intersections. The excess pressure vents off in predictable ways, producing a reliable binary output. The grid naturally forms working logic gates, capable of performing rigorous computation. Once a system can process information, it can store instructions. At higher scales, this programmable logic weaves together into compact geometric shapes that read their own structure and build copies of themselves, like biological DNA. In extensive ecosystem trials, researchers simulated competing species of these self-replicating shapes, placed right next to rigid, functioning logic gates. The biological swarm mutated and grew chaotically, yet the logic circuits continued calculating with absolute precision. Biological life and deterministic computation function as parallel expressions of the same underlying geometric code. To see the true scale of this computation, we have to pull back from the microscopic circuits and look at the entire lattice at once. This visual shows a property called succession flux. Every time a logic gate fires, a wave packet moves, or a form replicates, it generates a tiny amount of mathematical exhaust. Across the entire grid, these billions of nodes create a cumulative outward pressure. The mathematical weight of all this localized processing pushes against the boundaries of the system. To accommodate the constant generation of new information, the entire geometric lattice steadily accelerates its expansion. When compared to actual data, the predicted expansion rate locked in, the mathematical exhaust precisely matches baryon acoustic oscillation measurements gathered by modern cosmological surveys. This constant accumulation of computational waste is the literal source of the universe's expansion. Dark energy is the thermodynamic exhaust of a universe that is constantly thinking. This leaves one final question. Why does our reality run on this exact set of rules? Could a different computational boundary have created a stable universe? To find out, researchers built the Anthropic Gauntlet, a massive stress test placing hundreds of isolated environments under different cellular rules to see which ones could sustain an expanding cosmos. Nearly all the rule variants failed catastrophically. The highly permissive rules exploded into chaotic noise, while the restrictive ones instantly froze into solid blocks. Out of the 174 tests run, only 2 very similar rules successfully generated stable, expanding universes. However, the 2 rules differed in how they handled complexity. Under extreme computational load, the simpler rule fractures. While it can drive a basic expanding cosmos, it cannot sustain complex information or memory. Only the second rule possesses immortal memory, a specific fault tolerance needed to absorb microscopic fluctuations. It is the only code capable of maintaining stable geometric structures and complex calculations simultaneously. The specific rule required to protect a single memory from breaking is the same code driving the expansion of the entire cosmos. Our reality expands because it is uniquely optimized to think.